Our chapter 7 is on rational expressions. A rational expression is any expression with a fraction in it, basically. The word rational is just like the word fractional. Anytime you have a variable in the denominator of a fraction, you have what's called a rational expression. And you'll note that these aren't polynomials, because polynomials can't have variables in bottoms of fractions. And today we'll be mostly simplifying rational expressions. But one thing you have to worry about with any expression, but a rational one in particular, is under what scenarios are you dividing by 0? We aren't allowed to divide by 0. It's not something that math lets us do. So you have to think here in each fraction, what value of x would make it so I was dividing by 0. In this first one, it's -3. If x became -3, we would have -3 plus 3, which is 2 over 0, which is undefined. This should have been a 2. And it's not allowed. We can't divide by 0. So in this fraction here, x cannot be -3. And in this fraction here, x cannot be 0. And this fraction here, I can't really tell what x can't be yet. Gosh, I'm sorry, excuse me. I'm going to look at the bottom and factor it. I have a quadratic. And the bottom can factor into x plus 2 and x plus 1. The top I could try and factor. I'm not going to bother with it right now. I'm pretty sure it doesn't. Since the bottom factor into x plus 2 and x plus 1, I know that x cannot be -2 and x cannot be -1. Because if x is -2, if I plug in -2 for this, I get 4 minus 6 plus 2, which is 0, which means I would have 0 on the bottom of a fraction, and I can't have 0 on the bottom of a fraction, so here x cannot be -2 and it cannot be -1. That's excluding values from the domain that would make it dividing by 0, which we can't have. Whenever you do a rational expression problem, you have to find what values of x can you not have that would result in you dividing by 0. So now let's start simplifying. Here's the most common mistake with simplifying these. Students will see the 6 on top and bottom, and they'll try and cancel them like this to get x plus 1 over 1, which would just be x plus 1. You are not allowed to do that. You can't cancel just little bits and pieces of things. You have to cancel whole entire factors. Let me try and show why you can't do that. If x plus 6 over 6 was the same as x plus 1 over 1, which is x plus 1, well, that means that this should be true for any value of x. I could plug in anything for x and get a statement that would be equivalent to this. So let's say that x was 4. 4 plus 6 over 6 would be 10 over 6, which is 5 over 3. And that's definitely not the same as 4 plus 1 over 1, which would be 5 over 1, which is just 5. These are not equal to each other. You can't just cancel the 6's because the 6 has the x added to it. And so whenever there's addition or subtraction next to a variable, you can't just cancel the piece of the something. Over here, I can't cancel the 2x and the x, or the 6 and this stuff. There's nothing, I want this to be a 6. I can't cancel the 2x and the 6, or the 6 and the 6. But what I can do is factor the top. And the top factors into this. Now, this 2 and this 6 can cancel, because there's nothing being added or subtracted to them. They're whole entire factors. So the 2 and the 6 cancel. I end up with x plus 3 over 3. And those 3's cannot cancel. They cannot cancel because there's the addition next to the x. So if you ever aren't sure if you can or can't cancel something, plug in a number for x and then check the beginning problem and check your answer and see if they end up being the same. I'll show what I mean by that. Like, suppose I wanted to check to make sure that the steps I just did were correct. I could say, let's make x equal 5. Never pick 0 or 1 or -1, but 5, 2, 3, anything like that's fine. Well, 2 times 5 plus 6 over 6 would be 16 over 6, which is 8 over 3. If I plug in a 5 for this x here also, 5 plus 3 over 3 is 8 over 3, These two things are the same, which means my simplification was at least not wrong. It means maybe I could have simplified further sometimes, but I didn't do anything wrong, and that's how you can check, plug in a number for x in your original problem and your result. When you are simplifying, you factor everything completely, cancel common factors from top and bottom, and then make sure to exclude things that make the denominator equal 0. In this problem, there's nothing on the bottom that could make this equal 0. There's no x down there. Just like how with this one, there's no x on the bottom, so I don't have to worry about excluding things. Only when there's a variable on the bottom do you do that. I'm going to simplify these rational expressions. The first one we've kind of done before. Problems like this we've done. 3 divided by 12 is just 1 over 4. 2x's on top and 1 on the bottom is 1x on top. 1y on top, 3y's on the bottom is this. This is really x over 4y to the third, and I know that y cannot be 0. Because if y was 0, 4 times 0 is 0, and you'd get an undefined. This one, I'm going to factor whatever I can factor. The top can't factor, but the bottom can. I can put a 4, actually. Now I see what can cancel. The 6 and the 4 can cancel to give me 3 over 2. But the x and the 2x plus 1 can't cancel. So I'm left with 3x over 2 times 2x plus 1. Now the question becomes, what can I not have on the bottom because I've got a variable on the bottom? Well, I can't let this whole bottom piece equal 0. And I know that if 2x plus 1 were to equal 0, that would do it. So x cannot be negative 1/2. That's what x cannot be. Here's my simplification. X cannot be this. Here we have a difference of squares in the bottom. So I have a minus 5 over a plus 5 times a minus 5. These are whole factors that can cancel, so I cancel, and I get 1 over a plus 5, so a cannot be negative 5. Here is an important example that you're going to see a pretty decent amount of. If you have a minus b over b minus a, or anything of that form, like 3 minus x over x minus 3, 10 minus 8 over 8 minus 10. Whenever you have two things that are switched around and subtracting each other, this always comes out to negative 1. A minus b over b minus a is negative 1. Now, I can show why if you'd like. It's not really that important, but it can be useful to see. The b minus a on the bottom, I could switch around to be negative a plus b. This is the same as this. Then on the bottom, I could factor out a negative 1. And that means that these a minus b factors can cancel, and I'm left with just this negative 1. That means that 3 minus x over x minus 3, negative 1. 8 minus 10 over 10 minus 8, or other way around in this case. Wait, I can even calculate this. 10 minus 8 is 2. 8 minus 10 is negative 2. And that's just negative 1. They all come out to negative 1. Here, I can factor a 2 out of the top. And the bottom is x minus 9x plus 3. Factor the bottom. Factoring will not go away. It just always sticks around. These two things now can cancel. But when they cancel, you get a negative 1. 9 minus x over x minus 9 is negative 1. So we'll end up with negative 2 over x plus 3. We know that x cannot be negative 3. Lastly, here's a nice little word problem for us. We've done a problem like this in class way back at the beginning of the year. The rational expression below describes the cost in dollars to remove X% of the air pollutants and the smokestack emissions of a utility company that burns coal to generate electricity. I pulled this out of our math book, actually. One of the homework problems. The higher the percentage we want to pull out, the greater the X becomes. So like here, it says evaluate the expression for X is 20. That means we want to pull out 20% of the pollutants in the smokestack emissions. So we'll plug in a 20 for X. And It's going to become a 12 with 5 zeros over 80. And then I can at least cancel these zeros and get 4 zeros with an 8. And I can at least divide that by 4. I'm just going to reduce this kind of piece by piece. That gives me 30,000 over 2, which is 15,000. So if we want to take out 20%, that's going to cost us $15,000. Now let's take out 50%. And if I do 60,000 times 50 over 100 minus 50, well, I'm actually going to be a little smart about this. I'm not going to multiply the top out yet, because the bottom just becomes 50, and those can cancel. So this is just $60,000. To take out half the pollutants would cost $60,000. Now we'll plug in 80. So 60,000 times 80 over 100 minus 80 will become 60,000 times 80 over 20, and these can cancel to give me a 4 on top. 80 over 20 is 4. 60,000 times 4 is 240,000. Those would be our three costs. To take out 20% is 15,000. To take out 50% is 60,000. To take out 80% is 240,000. So those are actually multiplying by 4 each time. These reach an increase of 30% each time you jumped up by an increase of 30%. But the change did not go up in a linear fashion. This one up times 4 and this one up times 4. And it turns out the closer and closer and closer we get to 100%, to try and take out 100%, this gets astronomically expensive, to the point that it's actually impossible, right? X cannot be 100. If X was 100, 100 minus 100 would be 0, we'd be dividing by 0, which can't happen. Which suggests, based on this model, that it's impossible to pull out all of the pollutants from the smokestack emission. But even more so, it's financially unreasonable to try to pull out even 80%. That's a very, very high cost. It's tough to find the sweet spot for what's the best value for actually like eliminating the pollutants while not grossly cutting into any potential profits. So there is rational expressions. Thanks for bearing with me.